TrueHandling is a physics system for VR hand tracking. This is a project I actually did in 2018 for college, but I've just recently rediscovered it and wanted to post it online. So back in 2018, VR was widely adopted, but generally the only way to interact with the virtual world was using controllers like Oculus Touch. However, at the time there was one company called Leap Motion which made this sensor, which is basically like a little camera that tracks your hands. You can attach the sensor to a VR headset and actually see your hands in VR, which, compared to using controllers, is a really neat and liberating experience. The first time I tried it, I knew hand tracking was the future of VR, and being 2018, this was before Oculus came out with their hand tracking for the Oculus Quest. So there's two major components to a VR system which uses your hands for interaction. First of all, detecting and tracking the hands so the computer actually knows where all your fingers are and can draw them in the virtual world. That's what Leap Motion does. But the other thing is, in a physically simulated virtual world, having those tracked hands actually interact with objects in the virtual world in a realistic way is pretty challenging on its own. So in this project, TrueHandling, my goal was to make a realistic interaction system while using the Leap Motion to do the tracking part for me. Leap Motion does already make an interaction engine which addresses this, but I wasn't satisfied with it, which I'll explain later. So first of all, the way I decided to simulate the hands was to treat them as a set of capsule-shaped bones that move around. The way they're rendered in this clip actually matches the shape they're simulated as. So a really naive attempt at an interaction engine would be to just create kinematic capsule-shaped physics models to match the bones. Kinematic just basically means that they essentially move around with infinite force and aren't affected by any objects pushing back at them or affected by gravity or anything like that. This kind of system would allow you to lift up objects with a flat hammer and push things around, but if you actually try to wrap your hand around anything, it would just fly away because intersecting with your hand like that is basically an invalid position for the object. And this demonstrates one of the main challenges of creating a VR interaction system like this, which is that, of course, you can't actually prevent the user from moving their hands through things or otherwise give them any physical feedback. So the challenge is that users should be able to actually grab items and pick them up. Now, the way Leap Motion's interaction engine works is essentially like if you close your hand on an object, then the object gets stuck to the palm of your hand until you release it. It works fine for coarsely grabbing larger objects, but the problem is there's a total loss of your finger dexterity. You can't pick something up and rotate it between your fingers because the object can't move with relation to your palm at all while you're holding it. I didn't think that was good enough, so I made my own system, which is TrueHandling. I experimented with this problem for 2 months, and this is the best that I came up with. So the way my system works is, each one of the capsule-shaped bones is a trigger volume. When you touch an object, it computes exactly what point on the object you touched, the surface normal of that point on the object, and which point on the finger capsule bone touched it, and it keeps track of that until you're no longer touching. If the contact point happens to be inside of a different bone in the finger, it won't count it. When you touch the same object with multiple bones, it decides if the object is being held or not based on the different points you're touching and their surface normals. A simple solution is to check if any 2 points' normals have a dot product below some threshold, as if it's being pinched from 2 different directions, and keep the object held until that is no longer the case. A better solution is to project the direction between pairs of contact points onto the normals and threshold that instead, which prevents the object from being held in positions where it could easily rotate out of your grip. While an object is being held, an invisible target object is created and the actual object is constrained to it with a fixed joint. The target object is updated every frame based on how the fingers move. What it basically does is position the target object so that the centroid of all contact points on the object matches the centroid of those contact points on the fingers, and then it computes an orthogonal rotation matrix to minimize the squared error between each pair of contact points and rotates the target accordingly. The reason a proxy target object is needed is because, if the actual object was moved, then you could pull the object through the world, but with a proxy target object, the physics system can still prevent the actual object from being moved to an invalid position. One detail about this calculation is that I don't actually use the true physical contact points. Both the original point on the object and the point on the finger bone are projected onto the central axis of the capsule-shaped finger bone first. The purpose of this is so that you can roll your fingers on objects while holding them like this. The lines being drawn are between the contact points being projected like that onto the central axis of the bone. Another detail is that I actually add some extra points near the origin to the rotation calculation for each contacting bone. The extra points essentially try to keep the angle offset as close to what it originally was when the contact started. The reason that's needed is because when you're pinching an object with only 2 fingers, there's an arbitrary amount of twist between the 2 contact points. You need at least 3 different points in the calculation to fully constrain the solution. Finally, each one of the capsule-shaped bones also contains a kinematic collider as I described earlier, but with a slightly smaller radius than the trigger volume. This allows you to still interact with objects without picking them up. Objects that are picked up simply have collision disabled with these colliders. So that's basically how it works. Unfortunately, the result is finicky. I do blame some of that on the tracking quality of the leap motion sensor. The fingers can jerk around or just be in the wrong position, especially if it can't get a good view of your hands from where it sits on your headset. It is impressive how well the sensor works most of the time, but I think for this type of interaction system to really work well, the tracking would still need to be better. You'll probably notice that when picking things up, the virtual fingers appear to intersect with objects. To address this, I implemented forward and backward reaching inverse kinematics, which is meant to force the virtual fingers into a valid position. However, I disabled it because I wasn't happy with how it looked. One issue I had with the leap motion system is that surprisingly, there's no built-in way to calibrate where the sensor is in relation to your headset. If the sensor is in the wrong place, then your VR hands just won't line up to your real hands. The Leap Motion VR Developer Kit essentially just tells you to stick the sensor on the front of the headset without specifying exactly where, and that's especially an issue because the front of the Oculus Rift is rounded, and I didn't know if their default calibration was meant for a Vive or what. I also wanted to position the sensor higher and looking down with the idea that it might give better tracking quality if it can see your hands from a higher angle, which I made this little custom holder to do. The way I dealt with this calibration issue is essentially, you hold the actual Oculus Touch controllers like this in your hands, and you can see how the hands aren't aligned when it's not calibrated. And then, you hold down the triggers and move them around a bit and release. What that does is it tracks the point on the tip of your thumb and compares it to the reference point, which is on the tip of the thumbstick of the controller. Then it computes the offset by aligning the centroids and computing the rotation matrix like before. I also found that there's a temporal offset, which is a problem because moving your head around while leaving your hands still actually makes your virtual hands move around and hit things, but I didn't get around to addressing that. Another noteworthy issue is that the Leap Motion sensor can only track your hands in a limited field of view in front of the headset, so you can't interact with things to your side, and if you're holding something and then look away, it'll lose track of the hand. I didn't want objects to be dropped when you look away, so my simple solution is to just freeze missing hands at the last position they were in until they're seen again. One other interesting thing I did for this project was make this physically simulated rope. So the obvious way to do this is to just have a chain of capsule colliders with ball joints between each one. That actually doesn't work very well though if you have a lot of pieces in the chain. The trick I found to fix the simulation is to just add distance constraints between like every second link, then between every fourth link, then between every eighth link, and so on. So what that does is it makes it so that there are at most a logarithmic number of connections between any 2 points on the rope. And then, of course, there's a custom skinned mesh on it, so it looks good. So that's basically it. I look forward to seeing how VR hand tracking will improve over time because I think this is the future of VR.